All right, hey, I've got a couple questions from you guys. And this one here, let's see, chapter 30, number 14 is really a challenging one in the sense that it challenges your understanding about the B-ups of art law and the answer we got and how to use the angle. So at the risk of going too long with this problem, I really want to show you these angles because they can be a bit confusing. And so I want to start with the derivation of it. If you recall from the lecture video, I took a current flowing from left to right and then some point P above it. I drew a line perpendicular to the current from the point P, and then another line out to the beginning of the current, and I called that theta 1. And then theta 2 I defined as a line or an angle from these two lines, the one that is perpendicular to the current and the one that goes to the end of the current. That's important. Now let me not go through the derivation in this video, but in the lecture video as well as the author, the textbook, they give this equation for the answer for how to calculate the magnetic field. Now, it just dawned on me that I should look in the other book that I'm not as familiar with, the OpenStax book, because there's two ways of doing this. The second way, let me put a green equation for the second one, gives you cosine of theta 1 and cosine of theta 2. But they define their angles differently. So although they give you the same answer, you have to be careful which one you're going to use. And I know that in the survey book, as well as my lecture, I did this, and this is how I define the angle. So I'll say it again, be careful with theta 1 and theta 2. Here's how theta 1 is defined. From the perpendicular line back to the current and then out to the beginning of the current. That's theta 1. And theta 2 is defined between the two lines perpendicular to the current and out to the end of the current. And of course, what's also kind of interesting here is with this definition, we called a swing in a clockwise direction, so theta 1, as a positive number, and theta 2 as a negative number, so less than 0, when it's swinging in a counterclockwise direction. And that's kind of the reverse of what you normally see. But I wanted to review that because before I went forward here, because the problem itself is actually pretty straightforward because it is just made out of 3 straight wires. And so if this is the equation you get from 1 straight wire, then it's also the equation you would get from 3 straight wires. You just have to do this 3 times. And that's really what I want to emphasize. But more than that, I want to emphasize that angle. And then as I look at the solution, I realized, oh, this could really confuse some students because the person who did the solution used the cosine form, which was not derived in the textbook. And the cosine form uses this angle as theta 1. It's the angle between the r hat direction and the ds direction as you start B-ups of art. So in that derivation, if you remember, we actually started with this definition of the angle, theta 1 is between them, and about partway through the problem, we switched over to the red angle. So we started with the cross product of B-ups of art, which was this angle, and then eventually migrated to that angle. And then likewise, theta 2 would still be this angle back to the point and from the current. So here's the ds and here's the r hat, and so this is theta 2. So you could use either one of these equations, and the solution tends to use this equation I have in green. So I will show you it's the same thing, but I don't recommend this one. And so like a lot of these problems, they're, I think, hired people to do the solutions, and they may not even have access or even know or care enough to look at which way the author has presented it. And so this is one of those cases where the author presents it in this case, but the solutions are done in this case. And like I said, I'm not sure how the OpenStack. So I'm going to go back and look so I can have a better discussion with you guys on Friday, which might be a better method for you. But I'm going to mostly focus on that one. But I will show you it's the same as that one, since that's how the solutions did it. So keeping that in mind, let's look at the actual problem. The actual problem has this wire that comes down from some really far point out, goes across horizontal, and then goes back up really far. And the question then says, what is the magnetic field at some point? Let's call that the point P. And so why don't we make that then our origin here? Because they said this little, I'll call it a U shape to the wire, has a total width of 2a. So this would be a negative a, and this would be a plus a if this is the x axis. And then this distance here they label as d. Now, I should be careful back here with this original equation. I focused on what the angle was, but remember A is the distance away, which when we're looking at, when I'll label this as wire 1, and this is wire 2, and this is wire 3, wire 1 and wire 3 are a distance A away from this point, a perpendicular distance of A, but wire 2 is a perpendicular distance of D. And so this A is going to be A for both wire 1 and 3, but it's going to be a D for wire number 2. So keep that in mind. That could be easily skipped over and made confusing, given that we have an A in the derivation of an equation that we're going to then apply to our particular problem. And so we always have to be careful. Does the A in something we derived during the lecture match up the A in the problem? And usually not. Although in this case it looks like 2 out of the 3 times it does, but the other time it does not. All right, so why don't I begin with wire number 1 here and say, okay, so for wire number 1, if I write down the equation mu naught I over 4 pi, and then let me just pause again. The equation says A, the perpendicular distance away. And maybe I should even point out, this might confuse you because I derived it, and your author derived it with P kind of in between the 2 endpoints of the wire. But the same derivation would hold if we had put the point P here. We would just go down to here and call that A, and then we would draw a line back to there, and so that would be theta 1, and then we would draw a line to the end of it, and so that here would be theta 2. And that's kind of the problem I have here. It's probably best looked at it this way, that here's the point P, and so if I draw a line out to the beginning of this wire, this angle is essentially 90 degrees. And so this would then be sine of 90 degrees. And it swings in a clockwise direction, so it would be a positive 90 degrees. And then the perpendicular distance is that A, and so I'll put an A there. So the A here, the perpendicular distance is that A, sine of 90. Okay, then minus the sine of, and this would be theta 2. And here's where I kind of want to be careful. I have to draw a line from this point P where I want to get the magnetic field to the end here. So this right here would be theta 2. But notice it would be a positive number. It's not quite like this one where it swings in a clockwise direction. It swings in a counterclockwise direction. So unlike this derivation where I said theta 2 would be a negative one, in this case, right here, our theta 2 is a positive one. And I'll do you one better. Sine is then the opposite, and so this is opposite of it, which is a distance of D. So this would be a D. over its hypotenuse, which would this be its length here. And so I've got this A and D making a right triangle. So the hypotenuse would be a squared plus d squared square root. So putting this all together, I got mu naught I over 4 pi a. Sine of 90 degrees is 1 minus a d over the square root of a squared plus d squared. Okay, so there is my magnetic field from number 1. Now we should also do direction here. Coming to here, one of the right-hand rules, and there are many of them, don't confuse that with the cross-product right-hand rule, but an important right-hand rule at a chapter 30 here is if you take your right hand and kind of do the thumbs up, your fingers are curled and your thumb is straight. So if you have current that is curled, we don't in this problem, but if I did, I would put my fingers in the direction of the current and then my thumb would give me the field. And the reverse is appropriate for this problem. If the current is straight, then use your thumb for the current, and your fingers will give you the field. And that's what I have here. So I'm going to put my thumb in the direction of the current, and so my fingers are going to kind of curl around here. And so if my fingers curl around on the left-hand side, the field would be going in, and on the right-hand side of the current, it would be coming out. So I'd put X's here and dots here. And I guess I would do that in green, X's in and dots out for the magnetic field from wire 1. And this point P is over on the right, so this is going to be coming out. So back here with this equation, I'll say out, or if you prefer, I'll do a k-hat direction. And so again, this is the magnetic field from number 1. Now, I was going to go on to number 3, but I told you that I would do the green equation. So, not necessary, but maybe for your further understanding, let me do the green equation, because this is what your author is doing in the solution. In the green equation, as I mentioned here, the things are defined the same way, so A is still A, but what I would have is cosine of theta 1. And if you look at this, theta 1 would be this angle way over here between the beginning of the wire and the angle. And if this goes far enough out, that's 0. So this is cosine of 0 degrees. And then theta 2 is this angle right here. The angle between the direction of the last bit of current and the r hat pointing to that point. So this would be theta 2, if you're going to use the green one. And then cosine would be the adjacent, so that would be a d over the hypotenuse, so that would be an a squared plus a d squared. And you can see then that this actually comes out to be the same thing. Cosine of 0 is 1. We get d over the square root of a squared plus d squared. We would do this little right-hand rule the same way that we just did it, so we would get out, or the k-hat direction. And so sure enough, whether we use the equation with the sine of angle 1 and 2, and their definitions of theta 1 and 2, or we use the equation with the cosine 1 and 2, we get the same thing. But I'm going to encourage you not to do this one. I say that I should look at the OpenStax book first. But I derived it, and the Survey book derived it, as I said, by looking at this angles, the angle from the point of the magnetic field, not the points of the current. But either one would work, and so whichever one you like, use. That's fine. I just want to take a little bit of extra time and show you they are one and the same. Okay, let's go to wire number 3. I picked number 3 because I'm hoping you can kind of see number 3 would be the same as number 1. Now, it may not look like that at first. I mean, you do see that point P is the same distance from 3 as it is from 1, and they kind of have that same symmetry where it's up and over the same distance, although wire 3 is over to the right and wire 1 is over to the left. Or put another way, point P is to the right of the current, in number 1, but it's to the left of the current in number 3. So because of that, you might think the field is going to be in the other direction. However, the current also goes up instead of down. So that too would make me think it's in the other direction. So the opposite of the opposite is the original out direction. And it is. And I can see that by doing the right-hand rule. I'm going to take my thumbs up. I'm going to put my finger in the direction of the current. And I get this little curl to it. And that means on this side of the wire, the field is coming out. Okay. And on this side of the wire, the field is going in. And this point P is to the left of this wire coming out. So sure enough, I am going to get out at point P for number 3, just like I did for number 1. And everything else looks the same in terms of the magnitude, so I would think that I'm going to get the same equation. So during a test, or to save myself a little bit of time on the homework, I should just double the field from number 1, but I will show you that it comes out to be the same thing. It'll help you kind of see that it is, as well as help you understand what we mean by these angles. So let me put here this theta 1 minus this theta 2. Now, coming over here, we might then take this situation and maybe turn it to this way, because theta 1 is between the perpendicular line, there's theta 1, and the current. And in this case, it swings clockwise, so it would be a negative. So if I just said the sine of theta 1, and I'll say the absolute value of theta 1, would be its opposite. So that would be this length here, which is, well, maybe fit it better here if I put it here, d over the hypotenuse, which is the square root of a squared plus d squared. So that would be the sine of theta 1, but remember it is negative. And remember, sine function is an odd function, which means if I want the sine of a negative absolute value of theta 1, that would equal negative of the sine of the absolute value of theta 1. So that's a long way of saying this is really then a negative d over the square root of a squared plus d squared. And the mu naught I over 4 pi a. A is still the distance away, the perpendicular distance away. That's from there to the line of the current. So that's an a. And then this has minus, and then theta number 2 would be drawing from the point P way out here to where the current ends. And so wire number 3 ends way out here. And so this angle here, if you're drawing it really far, that would be a 90 degrees. But remember, it's swinging in the negative direction, the counterclockwise direction. So this is the sine of a negative 90 degrees. And of course, sine of negative 90 degrees is negative 1. With that negative makes a plus 1. So I'd get a mu naught over 4 pi a. And I'll take that and put it first, plus 1, and then minus d over the square root of a squared minus, or plus d squared. And so sure enough, after going through those angles, I get the same equation that I got here. And I already did the right-hand rule to show you it was out. So yeah, sure enough, number 3 gives me the same thing as number 1. Now, at the risk of taking too much time, maybe I should pick up my green pen and say, well, would I get the same thing if I did the way the author is doing it? The author's to the solution manual, not to the textbook. And he uses the other definition, and I'll do that in green. And sure enough, you will. I'll show you at the risk of making this problem look harder than it really is. And it already is hard. But if I do the mu naught I over 4 pi a cosine theta 1 minus cosine theta 2, and I'll write it in green to keep in mind we're talking about the different definition of the angle. A is still the perpendicular distance away. So again, coming back to original drawing, this is still the perpendicular distance away, which is labeled as A. So nothing new there. But remember that our definition of theta 1 right here is the angle between the current and the line going back to point P. So in our problem, here's the original current, and here's the line going back to point P. So that would be theta 1. And theta 2 is this angle here in green. It's the angle between the end of the current and the line going back to point P. So in here, way out here is the end of the current, and this is the line going back to P, so this would be the angle. And we're talking about 180 degrees there. So this would be cosine of 180 degrees. We're going to have to give this one, I think, some more thought here. So I'll just write it as cosine number 1. Because this cosine of number 1, so here's number 1 again, cosine number 1 is 90 degrees and a little bit more. Well, let me just use the Greek letter delta, lowercase delta, for that little bit more. So this is actually then cosine of 90 degrees plus delta. And then maybe for a cosine of 180 degrees, I'll just put in the -1. Now, if I do that, I'm going to go to one of those trig identities. The cosine of two angles added together is the cosine of the first times the cosine of the second, minus the sine of the first times the sine of the second. And then these two negatives, I'll just make a positive. And this simplifies a little bit because the sine of 90 degrees, no, I want to do this one first. Cosine of 90 degrees is 0, so that one goes away. And the sine of 90 degrees is just 1. So this just becomes a negative sine of delta. That one goes away, and I'll put the +1 first. And so now I can finish this green one, which, like I said, really wasn't necessary because we got it with the red, which we didn't even have to do the red one. We can just double the first one. But I want to show you it's the same. But if I come over here and go sine of delta would be opposite, so that's d over the hypotenuse. So d is the opposite over the hypotenuse, which is the square root of a squared plus d squared. Ta-da! And so, sure enough, I got the same thing with the green equation using their definition of theta 1 and theta 2 being a little different than the red equation, which their definition of theta 1 and theta 2. So, again, doesn't really matter which one you want to use, but I'll keep saying I like this definition that I'm writing in red, the one I derived, and mostly because that's what the author did. To be honest, I learned it with the cosines, and I always liked the cosines. And when I saw Survey do it, I go, I don't like that. But I found out that if I didn't stick to the way the author in the book does it, I just confuse students more. And that's what I'm finding in this problem. When I saw the solutions done in the cosine, I like, oh no, that's going to be a recipe for confusion. So maybe I better make a solution for it. And then maybe I better make a long solution for it and talk about how you can do it either way. But again, you wouldn't want to do it both. So either do it in red or do it in green. So just to summarize, because I've been talking now for 24 minutes, that I've done the first wire and got this one. And like I said, during homework, you could just have doubled that and move on. You didn't have to do the green, and you didn't have to redo wire number 3. Now, wire number 2 is a little bit harder. Well, maybe. I should just say it's the same, but it's different. So coming back to our picture, now that I've drawn on this picture so many times, I hope you can kind of see. But wire number 2, I would start off and jump to the, I'll call it the master equation that we derived, mu naught times the current. I should point out it's the same current. This really goes back to our current on our, or our physics on our electronics. This would be in series. So the current that came down here made a bend, and so the current in wire 2 is the same as wire 1, which is also the same as wire 3. I didn't say that, but that was kind of implied in these equations, that the current is the same. The thing that's interesting, though, is remember A is the perpendicular distance away. And so looking at wire 2, this is the perpendicular distance away. And so that should have a D in it instead of an A in it. Because, again, that's the perpendicular distance. And so that's always confusing and goes back to my famous phrase I like to say, make sure you read the math, don't just do the math. What does A actually mean in here? Because you can get into a problem like this that has an A in the definitions of things, and you might think, well, that A is the same as that A, and that is not at all what it is. A is that perpendicular distance away, so it would be a D for wire number 2, although it was an A for wire 1 and 3. Okay. Then we could say it's the sine of theta 1 minus the sine of theta 2. This will give me a chance to show you the definition of theta 1 and theta 2. Again, coming back to here, here's the definition of theta 1 and theta 2 in the red. Here, if you look back here, it looks almost like it. It's just our point is below the wire instead of above it. We do have a current going left to right, so number 2 is left to right. That's good. But our distance is below it. So maybe the best way to look at this, and if I draw a little thicker here, it'll bleed through, and I'll turn it over. Because now the current is going across here, left to right. The point P is above it, and the theta 1 would be a line drawn to the beginning current. And so that would be the theta 1. So I flip it over, this would be the theta 1 to the beginning of the current and the perpendicular. Okay? And of course, this would go in this direction, and so it'd be a positive. And that's kind of hard to see when you label it in this way, but it is a positive. Okay. And so there's our positive. Okay, so with that in mind, I can just say, well, theta 1 is the opposite. And so the opposite of this is an A, and then over the hypotenuse would be A squared plus D squared, square root. And then I've got a minus, and then theta 2, kind of the same thing. Theta 2, if I turn it over this way, you can see it better. There's the line going to the end of the current. There's the theta 2. Flipping it back over, then this would be the theta 2. And then hopefully you can see that is a negative value. That's our definition up here. Theta 2 would be negative if it swings in a counterclockwise direction. So I'll leave the negative here, but you might then say it is equal to the sine of the negative of the positive value of theta number 2. Because again, sine is an odd function, so the sine of a negative is then the negative of the sine. So I'll put that negative together with that negative, and then just have sine of theta 2 as an absolute value, and the sine of theta 2 would be the opposite, so that's an A, over its hypotenuse, which is the square root of A squared plus D squared. And then those actually end up being the same number. So this just becomes mu naught I, and I'll just put a 2A in the numerator that has a common denominator of the square root of A squared plus D squared, and I have the 4 pi and the D. I might talk about the direction. Here's where the right-hand rule is going to come into play. And so I'm going to make my thumbs up with my right hand. And again, look at the currents, the shape you have. Do you have curls or do you have straight lines? I got straight lines. So put your thumb in the direction of the current, and your fingers will give you the field. So if I do this, on this side of the wire, it's going in. My fingers go in, and then the fingers wrap around, and my fingers come out. Okay, but it's going in. And so I would have to say in, or if you like, negative k hat. So I have 3 fields, coming back to the first page. Going out is number 3 and number 1. They are the same in magnitude, and they're both coming out. But now going in is this one. Now, again, at the risk of talking too much, I should probably show you this same equation in the green. And so if we wanted to get the magnetic field using the cosine, we certainly could. And so B equals mu naught I, and let me go 4 pi, and then let me just kind of go back. If we're going to use this definition in the green for theta 1 and theta 2, we got to look at the angle between the current and the line back to point P, not the red one where it's the line from point P back to the current. Now this is still the perpendicular distance away. And so notice that for line number 2, that is a D. That's the same thing, we said at the beginning of deriving it using the red here. We said it was a distance of D. So that's still the same. But now we have to get the cosine of the angle. And again, it's probably better to flip it, because then this would be theta 1. This would be the angle between the beginning of the current and the line back to point P. So cosine of that would be the adjacent. So this is the adjacent. This would be A over the hypotenuse, which would be A squared plus D squared. Then we would have minus cosine number 2. Now, cosine number 2 would be this angle right there, the angle between the end of the current. So there's the end of the current, there's the ds, and there's the line back to point P. Now, I think this is probably best done by now calling this little angle the delta for a second, because I could then write this as cosine of 180 minus the delta. And so there's my delta. And like I said, at the risk of taking a little too long, but showing you it still works, I can do the trig identity. It would be cosine of the first. When you add 2 angles, times the cosine of the second, minus the sine of the first, times the sine of the second. Now you might have noticed in my algebra I treated this as 180 plus a negative delta. So I'm adding 2 angles together, but the second angle is a negative delta. So that's the formula then for adding 2 angles together, trig identity. But again, I want you to see that this green will come out right. The sine of 180 degrees is 0, so that term's going to go away. The cosine of 180 is a negative 1, so with that negative makes a plus. And then this cosine of negative delta is actually just the same as delta because it is an even function. It's not like we've been doing with the sines where it's an odd function. And an odd function meant we can, take the positive value of the angle and put the negative out front. An even function means f of x is equal to f of negative x. So we can just ignore the negative for any even function. And so that's what I'm going to do. I'm just going to ignore the negative function, or the negative part, and call it cosine delta. Okay, so if we come back to our picture, cosine of delta is the adjacent over the hypotenuse. So the adjacent is the A, and the hypotenuse is the square root of a squared plus d squared. So these are the same as we expected, because we had already done it over here in the red and said that they come out to be the same. So it's not a surprise that when we do it with the other definition, we get the same thing. And so this becomes a mu naught I, and then these two can be added together, so it's a 2a. But we still have the 4 pi d, and then we have the square root of a squared plus d squared. Yay! Okay, so sure enough, we have it. And I'll say it again. You don't want to do both these methods. Pick one you like better and stick to it. I'm going to encourage you the red. But like I said, because the author did it in green, I go, oh, this is really going to be confusing for students, and I'm just going to make a long-winded video and say, okay, what is the definition of these angles? Okay, so all the way back to the very beginning, right here. Either learn the one with the sign and where the angles are defined, plus or minus, or use the one with the cosines if you prefer, and again, learn where they're defined. I suppose the good thing is they're always positive, so that's makes that part a little bit easier. And they're the same as you get from the B's of arc cross product. So that's why I always have really liked this one in the past. But the author has felt that these are better for some reason. Like I said, I learned the green one when I was in school, and your author does this red one. But it's about a 50-50 mix. You pick up any textbook, they'll be half and half. That's why, again, it doesn't surprise me that whoever did the solutions did this one. About a 50-50 odds. And but your author has it in this form. And again, that's why I'm going to look at the Survey book. I mean, the OpenStax book. I'm kind of curious which one they decided to do. But I'll do that after I post this solution. Anyways, so now we can wrap it up finally. The final answer here is let's find the total field. And the total field is the field from wire 1 plus the field from wire 2 plus the field from wire 3. So we've got the 3 wires to add together. And we already said it and proved it, and I'll just repeat it, that over here we were showing that the field from 1 and 3 are exactly the same. So I'll just put 1 and 3 together and say it's 2 times, and I'll just write down the field from number 1, mu naught I over 4 pi a times 1 minus a d over a square root of a squared plus a d squared. And of course, that's in the k-hat direction. Okay. Then, field number 2 we derived, and it's in the minus k-hat direction, so I'll put a minus. And this would be a mu naught I over 2a. all over 4 pi d square root of a squared plus d squared. And then, of course, that's also in the k-hat direction, and the minus is why I put it here. And as I look at this, I see that the 2 can cancel a little bit with the 4, leaving me with a mu naught I over a 2 pi as common factors in both of these. There's the mu naught and 2 pi, and then there's the mu naughts, the I, and the 2 pi. And then, so there's an a here, but a d here. So if I put this a in here, this would be a 1 over a minus a d over an a square root of a squared plus d squared here. And then minus, and over here it looks like I've got an a in the top and a d in the bottom and a square root over a squared plus d squared. And of course, k-hat direction. And like any set of fractions, the best thing to do is to get a common denominator. So it looks like a times d times the square root of a squared plus d squared is the common denominator. And so this first term already had an a, so we would be multiplying by d times the square root of a squared plus d squared to get that one. Minus, and it looks like we already had an a and the square root, so we'd be multiplying by a d, so that'd be minus a d squared. This one already has everything but the a, so that would be then an a squared. And that would be, I guess, the answer. And I'm just glancing up at his solution. I don't know if I like the way he finishes the problem, but I wasn't real crazy about the way he did the cosine either. I would stop there and say, I'm done. For whatever reason, he changes the sign at the end. I'll just put the 2 pi and the a and the d and the square root of a squared over d squared here. And he factors out a negative. So this then becomes an a squared plus ad squared minus ad over the square root of a squared plus d squared. And then he factors out that negative and he puts it here with the k hat. And then he writes the words away from you. So he writes it in the negative direction as the final answer. Probably because you could show that a squared plus d squared is always greater than those. So that number is positive and then it's away from you. So I guess it makes sense why you would do it that way. It just, well, maybe that's good. The person who did the solution was reading the math, not just doing the math. Well, like I said, it was kind of long. Wow, 42 minutes. But I hope the two big things, and I'll just say it again to wrap it up, is that what I really wanted to show is the definition of theta 1 and theta 2 and when is it positive and when it is negative. And encourage you then to use this form, sine theta 1 and sine of theta 2. But it also point out, don't let the answer confuse you because your author uses this form and he uses a cosine and then that uses a different definition of theta 1 and theta 2. So you can do it either way. Bye now.